Our next speaker is Tine Celcer. In 2010, Tine has received a PhD in electrical engineering on telecommunications at the University of Ljubljana, Slovenia. His professional path then led him to CozyLab and from there to PSI, which he officially joined in 2013. Currently, he is the head of the experiment integration group with the control section, and among other responsibilities, he also supports the Tomcat beamline in SLS, where the GigaFRoST detector is being used. He will give us a talk titled GigaFRoST, Gigabyte Fast Readout System for Tomography, Control and Data Acquisition System Design.
Thank you. So before explaining what GigaFRoST is, I would first try to answer the question, why GigaFRoST? So some users that come to the tomography beamline at SLS, they want to observe fast dynamic processes inside of a sample. And for that, they need high spatial resolution as well as high temporal resolution. And in order to do that, the beamline was, before we had GigaFRoST, the beamline was using a commercial CMOS high-speed camera called PCO Dimax. This camera has very good characteristics in terms of small pixel size, big enough sensor, and ability to provide kilohertz frame rates. However, it has one big problem, which is common to all commercial cameras, and this is it has onboard memory. So the time of your scan is limited with this onboard memory. And in such experiments, we're talking about several tens of terabytes per day. So you can imagine that the beam time, or not the beam time, but the scan was very short. In practice, this was roughly 30 seconds. So then the users could go for a long coffee break because they needed 30 minutes to transfer the data from the camera to the beamline storage. So you can imagine it was not a very efficient beam time. So the idea came up, why not using the camera that has same characteristics but can continuously stream and stream the data directly to the server without any onboard storage. And this is how we then designed GigaFRoST. What we did is we used the PCO Dimax imaging chip because it provides good characteristics, so we wanted to build on that. But around it, we built custom-made electronics, which enables us to achieve this goal and be able to continuously acquire and stream data to the backend server at roughly 7.7 gigabytes per second. At the same time, we can provide a live image preview stream, which is also handled by the backend server. Okay, so how does GigaFRoST look like? You can see two photos of the stripped GigaFRoST camera without its housing. So you can see the headboard and the sensor. The sensor is split in 4 quadrants, and there are 2 data readout boards which are connected to this sensor. And each data board has 2 FPGAs. And each FPGA is responsible for reading out the data of one quarter of the image. Then when the data is read out to the FPGA, there's some on-the-fly pixel correction being done. And after that, this data is split into 2 streams over 2 10 gigabit fiber optic connections via UDP protocol. And this is connected directly to the dedicated backend server. So altogether, we have 4 FPGAs, which means 8 10 gigabit links. A next component is a control board, which also has an FPGA and a power PC, which runs an embedded Linux operating system. And this control board is, of course, responsible for controlling and coordinating the camera and the acquisition. It is equipped with a single 1 gigabit Ethernet module just for communication with the camera, and with 6 BNC connectors, which through TTL signals take care of using versatile triggering modes to do image acquisition synchronization. A little bit about camera control. So, as I said, on the control board, we are running, this camera is integrated into our EPIX control system via an IOC that runs directly on the power PC on the camera. It is responsible for controlling camera parameters. It is responsible for monitoring the system, so reading out the different temperatures or voltages in different subsystems of the camera. It is also responsible for configuring this versatile triggering modes and some DAQ configuration that is used for the backend server. So this here you can see an expert CA-QTDM GUI panel that it is used by the users. We developed EPICS device support for the camera to integrate it into EPICS control system. Currently we support 5 different record types: analog outputs, inputs, binary outputs, inputs, and waveform records. This is pretty much everything we need so far. We designed it in a way that we have a EPICS dependent layer, and then we have a control system independent lower level driver that talks to the API, which is also built in-house or designed in-house. So this gives us this opportunity that any future requirements that would come from users would be easily integrated. How we write the data from the EPICS world to the camera, we use a 2-step approach for basically for the parameters that are needed for setting up the camera. So first, whenever the EPICS value in some parameter is changed, it is written into a local structure. And only when we process the overlaying master PV, the set of all parameters is written to the camera at once. And this is the same when we're reading out the data. Periodically writes the data into this local structure and then sends an IO interrupt to trigger the reading out of the parameters into the EPICS channels. There are some records that directly speak to the camera, and these are mostly used for resetting or shutting down the camera remotely, or we can also shut down or reset individual subsystems of the camera. One additional thing that is very handy is so-called in-sync flag, which just compares the values of the EPICS channels against hardware parameters. And if they are not in sync, then it raises a flag, and we can get the data from the hardware and write it to EPICS. This really comes handy after some reboots or something like that, when you're not really sure if what the user sees, is actually what the camera has configured. Okay, moving to data acquisition architecture. I already mentioned, so there are 8 10 gigabit links. You can see them with this red line, and they actually go through lossless switch via two 40 gigabit Ethernet connections to the backend server, which has 2 CPUs, and each CPU is responsible for assembling 1/2 of the image that is coming from the camera. And there are 4 independent receiving processes running on each CPU. And once this image is assembled, it is placed in a specialized ring buffer architecture that is made for high-frequency memory access. And once the whole image is assembled, this data is then published as a 0MQ data stream to the downstream consumers via 2 InfiniBand connections. Apart from that, the backend server also sends a live image preview stream, another ZMQ stream, which is handled independently. And this stream is actually, usually it's downscaled, but the user has a freedom to define how he wants to get this stream. So after we publish this 0MQ stream, there's a next process going on, file writing. There's a writer server, which is connected to the same InfiniBand switch. It subscribes to this 0MQ data stream. What it does then is packages images into HDF5 files, and it stores them on a GPFS file storage server. So, of course, there are some limitations. Currently, we still have some limitations. And the problem currently that we're experiencing is that we can write data or distribute data from the backend server downstream. Here we are limited with approximately 2.2, 2.3 gigabytes per second, which means that eventually when we're using these high data rates from the camera, what it means is that the internal buffers of the backend server will eventually saturate, and we're limited with the size of these buffers. We already identified some possible, let's say, some bottlenecks, and we're working on solutions for that. And ideally, of course, we would like to achieve this for rates that would reach 7.7 gigabytes, so that we can continuously stream and be basically limited only with the size of the final storage. So Now I would like to just quickly present supporting infrastructure and basically how the GigaFRoST camera is integrated into the beamline infrastructure, especially how the image acquisition synchronization works. So I already presented the GigaFRoST, but there are, of course, other devices that take part in the experiment. The main device, I would say, the main thing is a sample which rotates on a Aerotech fast rotation stage. This stage is also integrated into the APEX control system via a APEX IOC running on a Windows PC. And what is special about, or let's say special feature of this rotation stage is it provides a so-called position synchronized output, which means that basically the user can configure when the TTL signals will be sent based on the angle of the rotation stage. And then, of course, we have some other external devices, like a millisecond shutter, for example, or any device that user might bring and would want to use, for example, as a master of the whole acquisition process by triggering some events when the acquisition should start. So we have TTL pulses, or TTL signals, that are somehow have to be efficiently distributed between all these devices. And in order to do that, we developed a so-called signal box. This is a simple FPGA-based device, which is integrated into our control system via a serial link, this stream device. What this signal box has is several inputs, for example, for the Aerotech inputs, outputs, and then several other inputs and outputs where other devices can connect to. And what we can do is we can dynamically define input-output pairs between these devices to efficiently route the signals across all devices that take part in the experiment. One can connect one input to several outputs because you want to trigger different devices with the same input. And what is also important here is for each single output, we can define an arbitrary delay in up to microsecond resolution, because often you want to trigger devices in sequence. Like, for example, you want to start opening the millisecond shutter a little bit before you start acquisition in order not to have images where you still see the millisecond shutter. So yeah, with this, I would slowly conclude my talk. I think I just scratched a little bit the surface of what GigaFRoST is. It's a very complex and I would say challenging project. It was, I think so far it was kind of a success story, but I would like to thank also everybody that contributed to this project. And there are many people that are involved here. Thank you.
Are there any questions? No. I had one. Sorry. No. Okay. So regarding this local structure that you were telling that locally you can then put some more information, is this information changeable online while doing the acquisition, so a client can change some parameters?
When I was talking about this local structure, this is controlling the camera parameters, not the data. There's no data there.
There is no
the data goes directly via this gigabit links to the. This is just like exposure time, delay, these kind of things. Which BNC input you want to enable, disable, how you want to trigger the camera. So this is everything done before you start actually the acquisition.
So then if the user would like to put some more information in the header, will go then in the central IOC that is merging everything?
No, it has nothing to do with data, no headers, nothing. It's pure control of camera parameters, nothing with the data vision. This is all done through the processes on the camera, backend server, and so on.
Okay.
You did answer it already.
Okay.
More or less the same question.
Okay.
Is there any other question? Okay, let's thank Dean again.
Thank you.